Hello, good morning everyone, to my fellow students, and of course to our instructor, Ms. Jovinal Bacaron. Good morning. So my assigned topic for this reporting was actually the continuation of Marilyn's report last week on chapter 2, which is all about the data center environment. And to be specific, the topics that I am going to tackle in this video would be all about the disk drive components, zone bit recording, logical block addressing, and the flash drive. So before I totally forgot, let me introduce myself. I am Maria Jona B. Abanyo, a fourth year BSAIS student under Black 2. Now let us continue. First, let us tackle the disk drive components. But before we will going to discuss or we're going to talk about its components, let us first define what is a disk drive. Actually, disk drive isn't new to us because we are now in the new generation era, the IT era wherein computer is rampant, computer is common nowadays. So what is disk drive really? A disk drive is a computer device that stores and retrieves information, data, files, programs, etc. from a disk. The key components of disk drives are platter, spindle, read-write head, actuator arm assembly, and controller board. So we will be discussing all of these components later on. So here is what a disk drive is. This is actually the disk drive. So disk drive is makita ni nato siya sa CPU. Kung i-open nato ang CPU, visible ang disk drive dito nga mao ni nag-store sa mga datas. And then if i-open ni nato ang iyang controller board, mao ni ang iyang image. Visible na nato ang platter, spindle, actuator arm, and the read-write heads. So all of these components mahimong visible if tangtangon ang iyang controller board. Now let us discuss its components. First, we have here the platter. So from the word itself, platter, the first thing that comes into our mind is a plate. And obviously it looks like a plate because it's round. A typical hard disk drive consists of one or more flat circular disks called the platters. The data is recorded in these platters in binary codes. So when we say binary codes, let's say for example, mag-type ka og letter A sa imong computer. Actually, dili letter A ang na-read ana sa computer but it's binary codes. So, let's say for example, the binary code of letter A is 01000001. For letter B is different, letter C, so on and so forth. And each characters on the computer have different binary codes. The set of rotating platter is held in a case called the head disk assembly. A platter is a rigid round disk coated with magnetic material on both surfaces, the top of and the bottom. The data is encoded by polarizing the magnetic area or domains or disk surfaces. Data can be written to or read from both surfaces of the platter. The number of platters and the storage capacity of each platter determine the total capacity of the drive. The second is a spindle. As we can see, the spindle connects all the platters and is connected to the motor. The motor of the spindle rotates with a constant speed. The disk platter spins at a speed of several thousands of revolutions per minute. The speed of a platter is increasing with improvements in technology, although the extent to which it can be improved is limited. The third is the read-write heads. Read and write the data from or to platters. Drives have 2 RW heads per platter, one for each surface of the platter. The RW head changes the magnetic polarization of the surface of the platter when writing data. When reading data, let's say for example this is the read and this is the write, or vice versa. While reading data, the head detects the magnetic polarization of the surface of the platter. During the reads and write, the RW head senses the magnetic polarization and never touches the surface of the platter. When the spindle is rotating, there is a microscopic air bag maintained between the RW heads and the platter, known as the head flying height. This air gap is removed when the spindle stops rotating and the RW head rests on a special area on the platter near the spindle. The area is called the landing zone. The landing zone is actually located in the lubricant to reduce friction between the head and the platter. So, ano ni siya napita makita ang iyang landing zone. Fourth is the actuator arm assembly. RW heads are mounted to the actuator arm assembly, which positions RW head at the location on the platter where the data needs to be written or read. The RW heads for the platter and a drive are attached to one actuator arm assembly and moves across the platters simultaneously. And the last component of the hard disk drive is the drive controller board. A drive controller board is a printed circuit board mounted at the bottom of the hard drive or hard disk drive. It consists of microprocessor, internal memory, circuitry, and firmware. The firmware controls the power of the spindle motor and the speed of the motor. It also manages the communication between the drive and the host. In addition, it controls the RW operation by moving the actuator arm and switching between different RW heads and performs the optimization of the data access. The next one is the physical desk structure. So this is the physical desk structure. Na niya ang spindle, ang track, cylinder, and also the sector. Data on the desk is recorded on tracks, which are concentric rings on the platter around the spindle. The tracks are numbered starting from 0 from the outer edge of the platter. The number of tracks per inch of the platter measures how tightly the tracks are packed on a platter. Each track is divided into small units called the sector. The sector is the smallest individually addressable unit of storage. The track and sector structure is written on the platter by the drive manufacturer using low-level formatting operation. The number of sectors per track varies according to the drive type. The first personal computer desk had 17 sectors per track, so recent desks have much larger number of sectors on a single track. There can be thousands of tracks on a platter, depending on the physical dimensions and recording density of the platter. The cylinder is a set of identical tracks on both surfaces of each drive platter. The location of RW heads is referred to as the cylinder number, not by the track number. Next was the second topic, which is the zone bit recording. Zone bit recording uses desk efficiently. This mechanism groups track into zones based on their distance from the center of the desk. The zones are numbered, with the outmost zones being 0. Here, 0 siya. An appropriate number of sectors per track is assigned to each zone. So a zone near the center of the platter has the fewer sectors per track than a zone on the outer edge. However, tracks within a particular zone have the same number of sectors. So this is a zone, this is a platter without zones, and this is platter with zones. See the difference. Logical block addressing. Earlier drives used physical addresses consisting of cylinder, head, and the sector. Number to refer the specific locations of the desk. The host operating the system and to be aware of the geometry of the desk used. Logical block addressing simplifies addressing by using linear addresses to access physical blocks of data. The desk controller translates LBA to a CHS address, and the host needs to know only the size of the desk drive in terms of the number of blocks. The logical blocks are mapped to physical sectors on 1.1 basis. Drive shown. So here is a logical block address, and this is the PE, physical address, CHS. Desk drive performance. Desk drive is an again, desk drive is an electromagnetical device that governs all the performance of the storage system environment. The various factors that affects the performance of the desk drives are discussed in this section. So first we have the desk service time. It is the time taken by the desk to complete an IO request. Components that contribute to the service's time on a desk drive are the seek time, rational latency, and the data transfer rate. Let us have first the seek time. The seek time, also called the access time, describes the time taken to position the RW heads across the platter with a radial movement, so moving along the radius of the platter. So in other words, it is the time taken to position and settle the arm on the head over the correct track. Therefore, the lower the seek time, the faster the IO operations. Desk vendors publishes the following seek time specifications, such as the full stroke, average, and the track to track. So full stroke, when we say full stroke, the time taken by the RW head to move across the entire width of the desk, from the innermost track to the outermost track. On the average time taken by the RW head to move from one random track to another, normally listed as the time of the third of the full stroke. And the last one is the track to track, the time taken by the RW head to move between adjacent tracks. Next, we have the rational latency. To access data, the actuator arm moves the RW head over the platter to a particular track while the platter spins to position the requested sector under the RW head. The time taken by the platter to rotate the position, the data under the RW head is called the rational latency. The latency depends on the rotation speed of the spindle and is measured in milliseconds. The average rotational latency is one half of the time taken for a full rotation, similar to the seek time actually. The data transfer rate. The data transfer rate is also called the transfer rate, wherein it refers to the average amount of data per unit time that a drive can deliver to the HBA. It is important to first understand the process of read-write operations to calculate data transfer rates. In a read operation, the data first moves from desk platter to the RW heads, then it moves to drive's internal buffer. Finally, data moves from the buffer through the interface of the host HBE. The written operation. The data moves from HBA to the internal buffer of the desk drive through the drive's interface. The data then moves to the buffer to the RW heads. Finally, it moves to the RW heads on the platter. Here is the process. We have the HBA interface buffer hard disk assembly. And this is the controller, internal and external transfer rate measures. In internal transfer rate, let's see the arrow, is the speed in which data moves from Platter's surface to the internal buffer. Ano na siya? Of the disk. The internal transfer rate takes into account the factors such as sync time and the rational latency. On the other hand, the external transfer rate is the rate at which the data can move through the interface of the HBE. The external transfer rate is generally the advertised speed of the interface. The sustained external transfer rate is lower than the interface speed. Desk I/O controller or organization. Utilization of desk I/O controller has a significant impact on the I/O response time. To understand this impact, consider that a desk can be viewed on a block box consisting of two elements. The first is the queue, the second is the controller. So the queue is the location where the I/O request waits before it is processed by the I/O controller. The desk I/O controller processes I/Os waiting in the queue one by one. The I/O request arrives at the controller at the rate generated by the application. This rate is also called the arrival rate. These requests are held in the I/O queue, and the I/O controller processes them one by one. Ano siya? I/O queue, I/O controller, then the request. One by one. The I/O arrival rate, the queue length, and the time taken by I/O controller to process each request determines the I/O response time. If the controller is busy or heavy utilized, the queue size will be large and response time will be high. Host access to data. So the next part that we're going to discuss was the host access to data. Understanding access to data over a network is important because it lays the foundation for storage networking technologies. Data can be accessed over a network in one of the following ways, like the block level, file level, or object level. In block level access, the file system is created on a host, and data is accessed on a network on the block level. In this case, raw disk or logical volumes are increased to the host for creating the file system. In file level access, the file system is created on a separate file server at the storage side, and the file level request is sent over a network as shown because the data is accessed at the block level. Object level access is an intelligent evolution whereby data is accessed over a network in terms of one of self-contained objects with a unique object identifier. Details of storage networking technologies and developments are covered in this section. This is the host access to storage. I have discussed the block level request and also the file level request. So this is a block level access and the file level access. Direct attached storage. DAS is an architecture in which storage is connected directly to the host. The internal disk drive of a host and the directly connected external storage array are some examples of DAS. Although the implementation of storage networking technologies is gaining popularity, thus has remained suitable for localized data access in small environments, such as the personal computing and work groups. DAS is actually classified into external and internal based on the location of the storage device with respect to the host. In an internal DAS architecture, the storage device is internally connected to the host by a series of parallel buses. The physical bus has a distance limitations and can be sustained only over a shorter distance of high-speed connectivity. In addition, most internal buses can support only a limited number of devices, and they occupy a large amount of space inside the host, making maintenance of other components difficult. On the other hand, external on the other hand, in external DAS architecture, the host connects directly to the external storage device. The data is accessed at the block level. In most cases, communication between the host and the storage device takes place over SCSI of FC protocol. Compared in internal DAS, the external DAS overcomes the distance and device count limitations and provides centralized management of storage devices. Native native command queuing. Wait for a moment. Command queuing is a technique. Disk native command queuing. So, command queuing is a technique implemented on modern disk drives that determines the execution order of the received IOs and reduces unnecessary drive head movements to improve disk performance when IOs received for executive at the disk controller. The command queuing algorithm assigned a tag that defines a sequence in which the commands should be executed. With command queuing, commands are executed based on the organization of the data on the disk, regardless of the order in which the commands are received. The commonly used algorithm for command queuing is seek time optimization. So here is an image without optimization, and this is an image of with seek time optimization. Without the commonly used commands are executed based on the optimizing read-write head movements, which might result in the reordering of commands. Without seek time optimization, so focus on this image. Without, I mean this one. Without seek time optimization, the commands are executed in the order they are received. For example, the commands are executed in the order of A, B, C, and D. The radial movement required by the head to to execute C immediately after A is less than what would be required to execute B. With seek time optimization, the command execution sequences would be A, C, B, D. Access time optimization Access time optimization is another command queuing algorithm. With this algorithm, commands are executed based on the combination of seek time optimization and an analysis of rational latency for optimal performance. The command queuing is also implemented on modern storage array controllers, which might further supplement the command queuing implemented on the disk drives. Now let us proceed to the last topic of this report, which is about the flash drives. So we have here the introduction to flash drives. With the growth of information, storage users continue to demand ever-changing performance requirements for their business applications. Traditionally, high I/O requirements were met to simplify using more disk. Availability of enterprises class flash drives has changed the scenario. So flash drive, also referred as solid-state drives, are new generation drives that deliver ultra-high performance required by performance-sensitive applications. Flash drives use semiconductor-based solid-state memory, flash memory, to store and retrieve data. Unlike conventional mechanical disk drives, flash drive contains no moving parts. Therefore, they do not have seek and rational latencies. Flash drive deliver high number of IOPs with very low response times. Also being semiconductor device, flash drives consume less power compared to the mechanical drives. Components and architectures of flash drive. Flash drive uses similar physical form, factors, and connectors as mechanical disk drives to maintain compatibility. This enables easy placement on the mechanical disk drive with a flash drive on a storage array enclosures. The key components of flash drives are the controller, interface, mass storage, or collection of memory chips, and cache. The controller manages the functioning of the drive, and the I/O's interface provides power to access data. Mass storage is an array of non-volatile, negated, and memory chips used for storing data. Cache serves as a temporary space or buffer for data transitions and operations. A flash drive uses multiple parallel I/O channels from its driver controller to the flash memory chips for data access. Generally, the larger the number of flash drive chips and channels, the higher the drive's internal bandwidth, and ultimately the higher the drive's performance. Flash drives typically have 8 to 24 channels. Memory chips in flash drives are logically organized in blocks and pages. The page is the smallest object that can be read or write on a flash drive. Pages are grouped into blocks. These blocks should not be confused with the 518-byte blocks in mechanical disk drive sectors. We have also here the features of enterprise flash drives. We have NAND, flash drive memory technology. It is a technology, and this technology is well suited for accessing random data. A NAND device uses BUD block tracking and error correcting code to maintain data integrity and provide fastest write speeds. The next one is the single level cells based flash. NAND technology is available in two different cell designs. A multi-level cell stores more than 1 bit per cell by virtue of its capability to register multiple states versus a single level cell that can store only 1 bit. The second is the write leveling technique. An important element of maximizing a flash drive's useful life is ensuring that the individual memory cells experience uniform use. This means the data that is frequently updated is written to different locations to avoid rewriting the same cells. If this in the device is designed to ensure that with any new write operations, the youngest block is used. Concept in practice, VMware and ESXi. VMware is the leading provider for a service virtualization solution. VMware ESXi provides a platform called Hypervisor. The hypervisor abstracts CPU memories, the storage resources to run multiple virtual machines concurrently on the same physical server. VMware ESXi is a hypervisor that installs on x86 hardware to enable server virtualization. It enables creating multiple virtual machines that can run simultaneously on the same physical machine. A physical machine that houses EXI is called EXI host. EC host provides physical resources used to run virtual machines. EC has two key components, the VM kernel and the virtual machine monitor. VM kernel provides functionality similar to that found in other operating systems, such as the process creation, file system management, and process scheduling. It is designed to specifically support running multiple VMs and provide core functionality such as resource scheduling, I/O stacks, and so on. The virtual machine monitor is responsible for executing commands in the CPUs and performing binary translations or BT. And that ends my topic. Thank you so much.